In 1843, Ada Lovelace wrote one paragraph that OpenAI's $100 billion models still cannot solve, and philosophers have a name for it: Lady Lovelace's objection. Alan Turing spent his career trying to refute her argument, and he failed. Once you understand why he failed, you will never interact with ChatGPT the same way again. Her exact words were these: "The analytical engine has no pretensions to originate anything, and it can do whatever we know how to order it to perform." That sentence landed on paper before the light bulb, before the telephone, before the automobile, back when Abraham Lincoln was still practicing law in Illinois. And that sentence remains the most accurate description of ChatGPT's fundamental limitation ever written. Lovelace never saw a computer and never typed a line of code. The machine she analyzed, Charles Babbage's Analytical Engine, was never even built. And yet she identified the exact architectural constraint that makes large language models hallucinate, that makes them confidently wrong, that has AI researchers at OpenAI, Anthropic, Google DeepMind, and Meta racing to solve a problem she articulated 180 years ago. Understanding her insight, and understanding why the greatest minds in computer science couldn't escape, it requires knowing who she was and what she was actually examining. Ada Lovelace was not making a philosophical guess. She was doing something far more rigorous, reasoning from first principles about what computation actually is. London in 1833 is where this story begins. Ada Byron, who wouldn't become the Countess of Lovelace until her marriage 3 years later, was 17 years old at the time. Her mother, Annabella Milbanke, had deliberately weaponized mathematics against poetry, and the reason was deeply personal. Ada's father was Lord Byron, the famous romantic poet who abandoned the family when Ada was 1 month old. Annabella convinced herself that poetry was a symptom of the Byron madness, that volatile and dangerous temperament she blamed for her ruined marriage. Mathematics became the prescribed cure, and this was no gentle redirection. Cambridge University in the 1830s warned that intensive mathematical study could cause psychological breaks. Annabella ignored the warnings because she would rather risk her daughter's sanity than watch her become another Byron. The finest mathematical tutors in England came to teach Ada, including Mary Somerville, one of the few women in Europe capable of discussing Laplace's celestial mechanics at a high level. Pure logic shaped Ada's entire upbringing. The plan worked, but not the way Annabella expected. Ada's imagination survived intact, and she fused it with rigor. She called her approach poetical science, using creative intuition to see structures that pure logic might miss, then using logic to verify them. A London salon in 1833 brought her face to face with a 41-year-old inventor named Charles Babbage. Babbage had become obsessed with a problem that plagued the 19th century: human error in mathematical tables. Navigation, engineering, insurance, and banking all ran on printed tables of logarithms, astronomical positions, and actuarial calculations. Humans called computers produced these tables, and that was the literal job title. Rooms full of people performed arithmetic by hand, copied results, and checked each other's work. Mistakes crept in constantly. Babbage discovered errors in the standard navigation tables used by the Royal Navy, and ships ran aground because someone miscalculated a logarithm. His first solution was the difference engine, a mechanical calculator that could compute polynomial functions using finite differences. Brass gears, cranks, and columns of numbered wheels made it work without electricity through pure mechanical logic. The British government funded the project. Babbage spent years on it, and the machine was never completed. A grander vision had already taken hold in his mind. He conceived something called the Analytical Engine, a machine that would not just calculate one type of function but accept programming. It would have a store, what we now call memory, and a mill, what we now call a processor. Punched cards borrowed from the jacquard loom, which used them to weave complex silk patterns, would feed instructions into the machine. Different cards would produce different operations, and you could theoretically make it do anything computable. Ada encountered the partial difference engine prototype in Babbage's drawing room when she was 19, and it captivated her. The Analytical Engine captivated her even more, though it existed only in technical drawings and in Babbage's imagination. An Italian mathematician named Luigi Menabrea published a paper in French describing the Analytical Engine in 1842, after attending one of Babbage's lectures in Turin. Ada received a request to translate the paper into English. Translation was only the beginning of what she produced. 7 notes labeled A through G more than tripled the length of the original paper. Note G contains what historians now recognize as the first computer algorithm ever written, a method for the analytical engine to calculate Bernoulli numbers complete with loops, conditionals, and a notation she invented specifically for the task. What made her exceptional was her refusal to get swept up in excitement. She did not project magical capabilities onto this hypothetical machine the way we project magical capabilities onto AI today. She examined the architecture, the punch cards, the store, the mill, and the operations, and she asked the question that mattered: what is this system actually doing? Her conclusion was that it processes instructions and nothing more. The analytical engine has no pretensions to originate anything, and it can do whatever we know how to order it to perform. That statement is not pessimism, but precision. She examined the architecture and found no mechanism for origination. Input, storage, processing, and output formed a closed loop where everything the machine produces follows from its instructions and initial conditions. No ghost hides in the gears, no spark of creativity, no genuine understanding, only transformation of inputs according to rules. 107 years passed before Alan Turing tried to prove her wrong. Turing published Computing Machinery and Intelligence in the journal Mind in 1950, and that paper introduced the Turing test, the idea that if a machine can fool a human into thinking it is human, then we should consider it intelligent. Section 6 of that paper contains something most people have never heard of: Turing's direct response to Ada Lovelace. He named it Lady Lovelace's objection, quoted her exact words, and attempted to refute them. Turing's counter-argument went like this: Lovelace was limited by the technology of her era and could not imagine machines complex enough to surprise their creators. Modern computers, Turing argued, already produce outputs their programmers did not anticipate. That surprise, he suggested, should count as origination. Here is why Turing was wrong and why Lovelace was more rigorous than he gave her credit for. Surprise and origination are not the same thing. A sufficiently complex system can produce outputs that surprise us because we cannot mentally trace all the implications of the instructions we provided. The outputs still derive entirely from those instructions. Our surprise reflects our own failure to predict, not the machine's creativity. The machine continues doing exactly what Lovelace described. Whatever we know how to order it to perform, we just ordered something too complex to fully anticipate. Lovelace was not making a claim about what machines would feel like to interact with. She was making a claim about architecture, and architecturally nothing has changed. ChatGPT runs on 1.76 trillion parameters, while the analytical engine would have managed roughly 675 bytes of memory. GPT-4 cost over $100 million to train, while Babbage spent £17,000 of government money and never finished his prototype. Architecturally, they perform the same operation. The parallel becomes clear when you line up the components. Punch cards fed instructions into the analytical engine, and training data consisting of terabytes of text scraped from the internet, books, Wikipedia, GitHub, Reddit, and academic papers feeds instructions into ChatGPT. The store held numbers for processing in the analytical engine, and context windows holding tokens, which are mathematical representations of words and word fragments, serve that function in ChatGPT. The mill performed operations on inputs according to the instruction cards in the analytical engine, and transformer layers with attention mechanisms perform operations on tokens according to learned weights in ChatGPT. Output in the analytical engine was determined entirely by instructions and input. An output in ChatGPT is determined entirely by model weights learned from training data combined with the prompt. The mechanism is identical while only the materials differ. When you ask ChatGPT a question, here is what actually happens. The model takes your prompt, converts it to tokens, and runs it through billions of parameters that training adjusted to predict the next most likely token. That token gets added to the sequence, and then the model predicts the next one, and the next one, and the next one, until a complete response emerges. Understanding and reasoning are not part of this process. What you are witnessing is extraordinarily sophisticated pattern completion. Billions of examples of how questions and answers fit together have taught the model statistical patterns about which words tend to follow which other words in what contexts. Reproducing those patterns in ways that feel meaningful is something the model does very well. Lovelace's insight, vindicated across nearly 2 centuries, is that the machine has no pretensions to originate anything. Every word ChatGPT outputs recombines patterns it absorbed from its training data. Remixing happens, interpolation happens, extrapolation along familiar dimensions happens. generating a genuinely new idea that was not somehow implicit in the patterns it learned, does not happen. Philosopher John Searle at Berkeley made the same argument in 1980 with his famous Chinese room thought experiment. Picture a person who speaks no Chinese locked in a room with a rulebook. Chinese characters come in through a slot, and the person looks them up in the rulebook, which specifies which characters to send back out. Someone outside the room sees what looks like fluent Chinese conversation, but the person inside understands nothing and is just following rules. Searle was arguing against a different target, the claim that running the right program constitutes understanding, but the insight traces back to Lovelace. Processing symbols according to rules is not the same as understanding symbols, and the mechanism matters. Most people miss this when they interact with ChatGPT. What feels like a conversation with an intelligent being emerges because the responses are contextual, relevant, and occasionally surprising. We project understanding onto that experience. Lovelace would have seen through it immediately and asked where the mechanism for origination is. Show me the component of this architecture that generates novelty not derived from inputs. We would have to admit that no such component exists. The insight that computation processes but does not originate explains the specific failures of large language models that frustrate users every day, and 3 of them deserve close examination. The confidence problem comes first. Lovelace understood something that most ChatGPT users do not. A computational system has no built-in way to know what it does not know. The analytical engine would have happily computed a result for whatever numbers and operations you fed it without pausing to say that the input seemed wrong. Instructions to add would trigger addition, instructions to multiply would trigger multiplication. No meta layer existed to ask whether the computation made sense. ChatGPT has the same blindness. Predicting the next token based on patterns is all it does, and if the patterns suggest a confident declarative sentence, then a confident declarative sentence is what you get. No mechanism for accessing ground truth exists in the model. No way to check whether its output corresponds to reality exists either. Whatever sequence of tokens has the highest probability given its training, and your prompt is what appears. The UK Met Office learned this lesson in October of 1987, when their weather model, architecturally incapable of expressing uncertainty, confidently predicted calm weather as the Great Storm approached Britain. Forecaster Michael Fish appeared on BBC television and told viewers not to worry because there was no hurricane coming. Winds hit 120 miles per hour that night, 15 million trees fell, and 18 people died. The model got the physics right and got its own confidence wrong, and it had no way to know that. Same architecture, same failure. ChatGPT will confidently tell you that a made-up legal case is real, cite academic papers that do not exist, and give you detailed directions to restaurants that closed years ago. The model is not lying because it has no concept of truth to violate. Pattern completion is all that is happening, and sometimes the most probable completion is wrong. Lovelace would have predicted this. A machine that processes instructions has no inherent error checking against external reality and can only be as accurate as its inputs. ChatGPT's inputs are patterns from text, not facts about the world. Making the model smarter is not the fix. Understanding the limitation is the fix. When you use ChatGPT, you are talking to a pattern completion engine rather than an oracle. The question to ask is not whether this is true, but whether this pattern matches reality, and answering that question is your job. The creativity illusion comes second. People use ChatGPT to brainstorm ideas, write stories, generate marketing copy, and compose music, and the outputs often feel creative because they surprise us and combine concepts in ways we had not considered. Creativity is not what you are looking at. Interpolation is what you are looking at. Millions of stories, millions of marketing campaigns, and millions of songs have trained the model to recognize probability distributions, to know what tends to follow what, which combinations occur together, and what structures are common. When you ask it to write a story about a detective who is also a pastry chef, the model is not inventing that concept, but blending patterns from detective fiction and culinary content according to learned probabilities. Lovelace identified this precisely. The analytical engine could combine and rearrange because that was the whole point of making it programmable, but the combinations would always derive from the instructions. Putting in cards for addition and multiplication would never produce a novel mathematical insight. You would get calculated numbers. Jazz musicians understand this distinction intuitively and talk about the difference between playing changes and playing music. Playing changes means navigating chord progressions correctly, hitting the right notes at the right times, and staying inside the harmonic structure. Pattern completion is what that amounts to, and a sufficiently trained player can do it on autopilot. Playing music is a different thing entirely. When Charlie Parker invented bebop, interpolation between existing jazz patterns was not what he was doing. He originated new harmonic structures that did not exist in any training set because he heard things that were not implicit in what came before. ChatGPT can play changes and navigate the chord progressions of language with stunning fluency, but it cannot play music or originate what was not already there. AI-generated content often feels subtly flat for this reason, technically proficient but missing something. What is missing is what Lovelace called origination, the introduction of something genuinely new that was not implicit in the inputs. When you use ChatGPT for creative work, treating it as an interpolation engine will serve you best. Exploring the space between ideas you have already introduced is something it can help with. The spark of genuine novelty has to come from you. The reasoning mirage comes third. When you ask ChatGPT to solve a math problem, logical-looking steps often appear. When you ask it to analyze an argument, something resembling reasoning emerges. The appearance of thought is the most seductive illusion of all. Lovelace's framing should stay in your mind here. The machine does whatever we know how to order it to perform, and nothing more. ChatGPT does not reason through problems but pattern matches to examples of reasoning it encountered during training. If your problem resembles problems in its training data, the pattern match will be good and the output will look like correct reasoning. If your problem differs subtly, the pattern match will fail, and confident nonsense that sounds logical will be what you get. ChatGPT famously struggled with simple arithmetic while writing eloquently about advanced calculus. And the reason is that the eloquent prose was pattern-matched from mathematical texts, while the arithmetic required actually performing computations, something the architecture was not designed for. Lovelace saw the analytical engine clearly. Computing was within its capabilities. But thinking about computing was not. No self-model existed, no mechanism for stepping back and evaluating its own operations. ChatGPT inherits the same limitation and produces text about reasoning without actually reasoning. The simulation of thought is not thought. When you need actual reasoning, supply the reasoning yourself and use ChatGPT to help express or refine it. Asking it to derive conclusions will only get you pattern matches to conclusions it has seen before. A question naturally arises at this point. AI is advancing rapidly, so won't some future version solve Lovelace's limitation and actually originate? The people building these systems are actively debating exactly that question. Sam Altman at OpenAI and Dario Amodei at Anthropic have both suggested that scaling might provide the answer, that enough parameters, enough training data, and enough compute might give rise to emergent capabilities that transcend pattern matching. They point to abilities that appeared in larger models that were absent in smaller ones, to emergent behaviors, to apparent reasoning. Yann LeCun at Meta disagrees. Geoffrey Hinton, the godfather of deep learning who left Google to warn about AI risks, remains uncertain. Genuine division exists within the field. Lovelace's framework clarifies the question. Her claim was not that machines will never be intelligent, but something more precise. This architecture cannot originate because it has no mechanism for origination. The question for future AI is not whether we can make models bigger, but whether we can design architectures with fundamentally different capabilities. More of the same architecture, meaning more parameters, more data, and more compute, produces more sophisticated pattern completion without producing a different kind of process. Making the analytical engine faster and giving it more storage would not make it do something its architecture does not support. Hybrid systems that combine language models with external tools, databases, and formal reasoning engines are where some researchers are focusing their efforts. And this approach is promising precisely because it acknowledges the limitation. If the language model cannot verify facts, give it access to databases that can. If it cannot reason reliably, connect it to systems designed for reasoning. Solving Lovelace's problem is not what this does. Routing around it is what this does. True artificial general intelligence, some believe, requires something we do not yet understand, an entirely different paradigm. Lovelace might agree with that view. Her claim was never that machines could never originate, only that this machine with this architecture can only do what we know how to order it to perform. A different machine might have different capabilities, but we have not built that machine yet. What a Victorian countess figured out in 1843, what Alan Turing could not refute, what John Searle restated in 1980, And what AI users in 2024 are still learning comes down to this. Computation is transformation and not creation. Processing inputs according to rules, no matter how complex the rules and no matter how vast the inputs, cannot produce genuine origination. Impressive outputs from a well-designed system prove the system was well-designed. Not that the system understands anything. The confidence problem, the creativity illusion, and the reasoning mirage are not bugs that OpenAI will patch in the next release. They are intrinsic to the architecture and represent what you get when you scale pattern completion to the limits of human engineering without adding a mechanism for genuine understanding. What Lovelace could not have predicted is that we would build her machine, hit her limitation exactly as she described, and then spend $100 billion trying to get around it anyway. That might be the most human thing about artificial intelligence. We see the walls, we know they are there, and we keep throwing ourselves at them. Lovelace's insight clarifies rather than discourages. Understanding the limitation lets you work with AI far more effectively because you stop expecting oracular truth and start verifying. You stop expecting creative origination and start providing creative direction. And you stop expecting reasoning and start doing the reasoning yourself while using AI to assist with expression and exploration. The best way to use ChatGPT is not to treat it as an intelligent collaborator, but to treat it as the analytical engine that Lovelace described, an extraordinarily powerful tool for processing information according to patterns, one that has no pretensions to originate anything. The next time you prompt an AI, ask yourself the question Lovelace would have asked. What are you actually ordering it to perform? Is that a task pattern completion can accomplish, or are you expecting origination from a machine that has no mechanism for it? The most significant innovation in AI is not GPT-5 or Gemini Ultra or whatever ships next quarter. Users who finally understand what these systems are represent the most significant innovation, and that understanding started with a countess in 1843 who looked at a machine that did not exist and saw its limits more clearly than most of us see the machines on our desks. Ada Lovelace, Alan Turing, John Searle, and ChatGPT connect across 180 years through the deepest question in computer science. Can machines think? Lovelace answered with precision. This kind of machine can only do what we know how to order it to perform. Turing tried to refute her and failed. Searle restated her insight for a new generation. Every time you watch ChatGPT hallucinate a citation or confidently tell you something false, you are watching her be right again. The question going forward is not whether she was wrong, but whether we can build a different kind of machine. Hidden structures connecting fields we think are unrelated are what this channel explores. From Victorian mathematics to artificial intelligence, from the philosophy of mind to the architecture of transformers, from the past illuminating the present. A 1970s basketball coach invented the algorithm behind TikTok's recommendation engine, and medieval monks anticipated information overload centuries before the internet arrived. Subscribe if you want to see how other historical figures predicted modern problems. Leave a comment below telling me about a question you asked ChatGPT where it gave you a confidently wrong answer, because I want to know what patterns it was matching to instead of thinking.